All right. Well, thanks very much for the introduction. What we're here to talk about today is something we announced 2 weeks ago called pCell technology. It's funny, it sort of leaked out a little bit unexpectedly 2 years ago because I was giving a talk at Columbia, and I should know a little bit more about the web and everything else, but I didn't realize I was giving a lecture that was going to be broadcast over the internet, and they asked for something new we were working on in the lab that not released yet. And I liked, unlike a lot of the work that's done where you kind of have what is a significant advance, and you kind of publish it and then you refine it and so forth. It gets released to commercial or standards bodies, et cetera, and then they go and polish it up and release it in some form. The usual way that I do my work is that we develop everything kind of like a startup and expect to release it and have it so it can be released commercially, hopefully within a year. And so that was the case with this, but since it got out, we released a very, very vague white paper about DIDO, D-I-D-O, distributed input, distributed output technology, without getting into any of the practical issues and so forth, just sort of explaining more than the few slides I had in that talk. So now that we have it out, we've been just kind of overwhelmed with people that are interested in it. And so we've been working on another white paper, which is much more detailed, goes into a lot more of the technology and so forth. But we are just doing nonstop demos. We had hoped to maybe do a demo here, but we just couldn't get into the room in advance because of all the classes. But I'd like to say, even before I start out on the talk, is that we don't really have anything we want to hide here. No one's trying to, some of the stuff are pretty significant advances, okay? And they deserve to be very closely examined. So, for example, I would invite people from Stanford. You're just in our backyard. I mean, we did most of the work actually in Palo Alto, then we moved up to San Francisco. To come up, maybe get a group of people who want to get a demo, dig in, really see what the thing looks like. It's too bad we don't have a demo here, right? But anyways, I have some videos of demos, all right? And very happy to go and show you what we've got. So this is the company. There's me. As you just heard, either you could say that I've been doing a lot of different things, or you could say I haven't been able to hold down a job. Either one is, I suppose, is equally true. But my background, I way back when developed QuickTime technology, web TV, which I guess maybe the significance of web TV was that we just showed that the web could be used in something other than a computer. You know what I mean? But in any case, that I got acquired by Microsoft, built their campus here. We developed all their television and television-related products. I did Color Macintosh, just did a cloud gaming company and so forth. Antonio Ferenza, PhD, is the principal scientist. He's been working with me for 8.5 years on this. And he got his degree at UT Austin. I started working with him when he was finishing up his PhD. And I had gone around to a lot of people then with the idea, with the simulation, and people would just turn me away. They're saying that, I don't know, what you learn in your first year of electrical engineering says a lot of the things you're trying to do here are just not going to work. And one professor, I remember, because I thought it was actually a reasonably sophisticated thing that I was putting in there. He said, "Who put you up to this?" And so, but anyways, when I contacted Antonio, we were able to go and he said he saw it really as a challenge. He kind of analyzed it to the point where he said that there's a few things that we're doing that are quite different that have been done before, and he wanted to go figure it out and work with me to make it a practical system. He was at IOSpan, with Paul Raj here, and Raycom, Samsung Freescale, so he has a great background. Roger's terrific guy for just putting together every imaginable kind of basic technology. The early algorithms for MOVA facial capture. It's used for gravity recently, but Harry Potter, where everyone turns into his face, Curious Case of Benjamin Button, and on live. And Cindy Ivor is actually in the audience here, who kind of holds the whole place together. Here's the team. Okay, so let's talk. We started this thing talking about that I tend to dip my toe into things that are big. Well, okay, let's look at mobile operator revenues. Here's very recent numbers. 2013, mobile operator revenues are $1.2 trillion US dollars worldwide. They expect that to grow to $1.4 trillion by 2020. Now, given the amount of infrastructure, everything else they plan to put in there, that's a pretty small increase, actually. As you can see, they see the overall mobile ecosystem at $2 trillion last year and growing to $2.9 trillion. And the reason they see operator revenue not growing that much is they see that the world is becoming more of a commodity world. With LTE being everywhere, even a T-Mobile can effectively compete very well against an AT&T and affect their prices and so on, because everyone's selling more or less the same thing. They do see big growth in apps and content and advertising, and then these numbers don't add up to these numbers, and everything in between, the infrastructure, the devices, and so forth, adds up to these very, very large numbers. And of course, all these numbers those big numbers are driving huge growth. We're already seeing that. This is a chart from Ericsson last year. And one of the things that I find really interesting about this chart is this pretty much tells you why the early adopters of LTE were FDD adopters as opposed to TDD adopters. The yellow bars there show the growth that we've seen in data from voice traffic. And this is really what they had in mind back in the early 2000s when they were planning the networks that are deployed today. No one imagined that they would see this massive explosion of data growth, which started with the iPhone, get amplified when Android was introduced actually around the same time as the iPhone. But when Verizon adopted Android and really said, hey, we're going to get behind this thing, then it really began to contribute to the huge growth there. And then with the iPad. And as you can see, this growth, as they see continue into 2013, they expect to grow well beyond that. So here's, again, Ericsson again. And you can see 2013 is where we are now. Look where they expect them to be, everything to be in 2018. What's nice about this chart, they begin to show how it's broken up, and you can see that it's highly asymmetric. The vast majority of it is, well, already more than half of it is video alone. Then when you look at things like web browsing is a lot of video. I mean, you go to a website, video comes in, and there's other mostly downstream activities. Sure, there's FaceTime and Skype and things like that are symmetric, but the vast majority of what we're seeing now is highly asymmetric. We actually have this San Jose thing. It's a really cool analyzer, and you put up in San Francisco, and you can listen into AT&T Verizon. Their downlink channel is saturated. The uplink channel is empty. Okay, we're already seeing 8-to-1, 10-to-1 in the U.S. And I think it's going to be pinning there because you need a certain amount of uplink just to be able to do the downlink, right? And there's no more downlink to be had. But look at this explosive growth. So then you take Cisco's numbers, again, just released in February. So if we make it 1x in 2013, by 2020, we're talking about 20x the amount of data traffic that we have today, 7 years from now, 20x. And so does anyone see any problem with this graph? Okay, well, here's the problem. Okay, seriously? I mean, how can we possibly handle 27x the amount of data traffic on mobile? And the thing that's funny about it, this is sometimes what happens when you have analysts who are going and taking this assumption and then building other conclusions from it. That $2.9 trillion, this is the foundation that it's built on top of, okay? They're tacitly assuming that there is a way to increase the capacity of current networks by a factor of 27. Let's go back. That means networks that have been built since the beginning of time for cellular are now going to increase by a factor of 27, okay, by 2020. Meanwhile, you've got all sorts of things, we'll talk about this, and even 10x in our view, it's beyond what you can physically accomplish using cellular technology. We're already at a point of overload in major markets, and it's getting worse. And it starts with being out of spectrum. I showed this chart here 2 years ago when it was released by the FCC. Everyone agreed with the upper bars about the growth. But it's funny, nobody believed about the bars going down here, that by 2013, we'd actually have places where we could not meet the demands, given the spectrum that had been allocated thus far. And it wasn't until Lowell McAdam, the CEO of Verizon, followed by his CFO, had to make disclosures to their investors saying that, hey, we cannot meet the needs in our major markets of New York, Chicago, San Francisco, Dallas, I believe, and the reason we can't is because of a physics limit. Now, how often do you see a CEO of a major corporation talk about physics to investors, okay? He basically, essentially what he was saying, and this is confirmed by the work they've done, they tried everything. They've tried all the different advanced modes they looked at with LTE. They've tried MIMO. They've tried small cells. They've tried different types of techniques for dividing up the cells, cooperative multipoint. They've experimented with everything. The whole world has come to the leader of the world, the most advanced wireless operator in the world right now, one of the largest deployment of the most advanced technology, with everything they got. And he felt he had to make a disclosure to investors to say that they had hit a physics limit, okay? And there's lots and lots of discussion. We can have a huge debate, and it could take much more than this session about whether or not there's other things they could tweak. But there's nobody on the planet who's going to and saying that the technology as we know it today can scale by a factor of 27 by 2020, okay? So if we look at current networks, they're already overloaded. A lot of people don't realize that LTE is really only 3 to 4x the capacity of 3G. And 5G is at a call for paper stage. I mean, people,
so can
yeah.
So, I mean, Qualcomm's saying they can do 1,000x with small cells. So there are people out there that are saying they can do much better than 27x.
So we have, one of the things that has been overwhelming in the last 2 months is the number of resumes that we've received from people who are doing actual small cell deployments for AT&T and Verizon and a couple other operators around the world. We've met with the small cell people. They talked about the deployment they tried to do in the baggage claim area of SFO and what it took to try to aim these things, avoid the small cell the interference they're having. So the problem you run into with small cells is this. I mean, it looks great in theory, not in practice. We ran MATLAB simulations and tried to explain to people the problem. I use this is not a great explanation. I'm talking to a technical audience. You deserve a better explanation than this. This is why I say the lay people, and that is, we made the cells smaller, but we did not start living cells smaller. We did not start living in dollhouses. In other words, the walls are just as thick as they used to be. If you put a bunch of small cells on telephone poles outside of buildings, they need a certain amount of power to penetrate the walls of those buildings. That amount of power in free space goes a pretty long way. Okay, it's not like you've got say a metro cell that is transmitting at pretty high power and is going both a reasonable distance that you can measure and control, and also is able to penetrate through the sort of buildings that we live in. That's not a complete explanation. There's more to it than that, and I want to say that well in advance. But I will tell you this. Let's set aside all the technology, set aside everything else. Look at any projection that there's been for small cell deployment. There's nothing close to it, all the way down the supply chain, all the way to the chip vendors who are trying to make it. Nobody has deployed anything close to what they thought was small cells. Yeah?
How much spectrum is there available that's been vacated by the TV broadcasters?
Is that related to small cells, or just about
Just the capacity.
Oh, well, I mean, it's nowhere near 27 times. I mean, practical spectrum being used today is, let's say, rough numbers, between 500 megahertz and 2.5 gigahertz. So that's about 2 gigahertz of spectrum, right? Well, let's say that everything all the way down to HF was vacated. That'd be 1/5 of, that'd be 500 megahertz, right? So I think, you know, we're pretty much out of spectrum. Okay. So you have intercell interference. Okay, then you have handoff interference issues. And again, handoff through, you know, these are something that's called metro cells, is very infrequent. Handoff through femtocells could be every second down a roadway, okay? Handoff is a huge amount of overhead. Then you get into the costs that they're running into, the zoning permits, the backhaul. In a cellular system, if a cell fails, that area loses coverage. It's not like the other cells can suddenly fill in, all right? You lose coverage. There's public safety concerns. There are no telephone booths around for things like, for emergencies. So that means that they really have to look at battery backup at the very least, and perhaps generators for all these cells. Not an unreasonable proposition for a large cell, but for every lamppost, okay, it's just not practical. Being able to bring power and so forth. But the other thing you run into is just in terms of the layout that you need to do. So then we can go and begin to look at stadiums. And this shows, the picture above is what Verizon was showing that they did for their deployment in the Denver Broncos Stadium. And as you can see, they tried to go and arrange the Wi-Fi in a cellular arrangement. And the trouble with Wi-Fi, of course, it's highly variable. It's subject to interference. It's very difficult to control. This sign was up at the Super Bowl in 2014, and they were inspecting people with a wand to see if they had their personal hotspot on to try to avoid any kind of interference. They also they blocked NFL.com, and they blocked all streaming videos, like getting on an airplane, okay? Even with all of that effort, they had 800% growth in usage of Wi-Fi from the previous Super Bowl. And some of the fascinating statistics are 18% of their traffic were iPhones updating themselves in people's pockets. So the amount of stuff that you run into these days in terms of the capacity is just overwhelming. And even look at that picture, of course, but the people on the edges of those little cells they've created have terrible service. The people in the center might get good service and so forth. So you just got a very highly variable situation. Be mindful of time here. Okay, so let's talk about pCell, all right? Let me run a video, which is on our website, but nonetheless we'll give you kind of an overview, and then I'll go into a lot more detail about it.
Smartphones, tablets, and laptops. They're just the beginning of an era where smart, internet-enabled devices of all kinds demand more and more mobile data at reliably fast speeds. We've added cells, improved networks, increased spectrum. But the truth is, our always-on connected world is running out of capacity. With demand for data projected to increase dramatically by 2020, the time has come for new thinking. The time has come for pCell technology. pCell is an entirely new approach to wireless designed to profoundly increase the data capacity of our finite spectrum. In an existing cellular network, each tower transmits a radio signal, forming a large cell and carefully avoiding interference with other cells. Mobile devices all share the cell's capacity, taking turns so they don't interfere with each other. This all worked great until everybody started carrying smartphones and tablets, streaming photos, music, and videos. Even with more spectrum and small cells, demand is far outpacing capacity, and we've hit a physics upper limit. pCell technology turns the whole problem inside out. Instead of dodging interference, pCell exploits interference, combining radio signals to synthesize tiny personal cells, pCells, of wireless energy around each mobile device. So rather than hundreds of users taking turns sharing the capacity of one large cell, each user gets an unshared pCell, giving the full wireless capacity to each user at once. It's nothing short of a revolution in wireless. Even in the biggest crowds, there is a pCell for every user device. And no matter where you go, you've got a fast, lag-free mobile connection. Simple, discrete pWave radios can be placed anywhere it is convenient, making cell towers a thing of the past. pCell technology realizes the dream of ubiquitous broadband connectivity. It changes the game, making it possible for thousands of fans to share video instantly. Delivering reliable video conferencing, whether closing a deal on Wall Street, showing your family the lights of Times Square, or smoothly streaming an HD movie for a 3-hour drive. With pCell technology, wireless is fast, reliable, always there. pCell technology from Artemis.
All right. So let me talk about what those things are and how they work. And let's see. Oh, good. On that thing. And then, oh, okay. So in an idealized cellular network, you have an arrangement like this. Looks like a honeycomb arrangement where you have the base stations in the center and they're all ideally spaced. And then what you end up in the real world is something more like what we have in the center picture here, where you just can't place things in ideal positions. There's obstacles and so forth. You might end up with a dead zone. And even though you do a really thorough job in planning your cellular system, if you had increased the size of any of those cells nearby, you would interfere with other ones. You have some cells that someone has a femtocell in the middle of a macrocell. Their apartment's working great. Their neighbor is screaming bloody murder because nothing works for them, right? So it really depends. pCell, it's a very different approach. What we say is let's go place the base stations anywhere. They can really be deployed randomly. They're deployed based on where the economics make it least expensive and convenient to deploy them. And they can have, they vary in their power level. In fact, they vary by millisecond. In fact, power, which is not a dimension you have much control over in a cellular system, like intercell varies slightly to increase or make the cell smaller in their SON technology. We vary the power enormously throughout the use of our system. So some of those coverage areas are bigger, some are smaller. It doesn't matter what they cover. Whereas this is largely an if-then technology. This is very much a mathematics technology. Okay, we don't do any if-thens. We don't have time for it, frankly, with what we're doing. If you then add users into both cellular and pCell worlds, the users are the red dots. As you can see, there's an unfortunate user in the dead zone there. You have some people that are near a cell center, and they're very happy because they have good performance there. There's some near the cell edge, which is not so great. You have that neighbor of the person who has the femtocell in their apartment who has great coverage from a small cell and a macrocell, and they're screaming bloody murder because neither of them, of course, allows them to receive a phone call. Then with pCell, then you notice if I go back, the coverage for cellular and the signal quality for cellular are the same thing. With pCell, the coverage and the signal quality are completely different. right? What happens is we have these overlapping signals, and the overlapping signals sum together. It's quite different than a MIMO type of structure where it's a base station-based system where the number of transmissions from the antennas is directly tied to the number of users. These antennas have a varying number of users that each of them are serving, some overlapping, some not. It's a user-centric wireless system. It's a different approach. And unlike MIMO, it's not cubic as it grows. It is linear. And unlike MIMO, it does not need to be cellularized or clustered. Rather, it's a pure coverage area.
Distributed MIMO.
Well, we haven't seen a distributed MIMO that goes to this scale.
He does it all the time.
He's getting linear results.
Bob Kahn had a project that was part of it way back, Distributed Sensor Networks. It was all in there.
Well,
Ask some of the participants there.
Well, it'd be great. We'd love to see the paper because we have every time we go.
For the reports, they're not all available.
They are.
Ask Bob Kahn for
Bob
what
Kahn.
is available from DARPA. And
All right. Well, I think I'm done with my talk then. Maybe Bob can give the talk.
It's okay, go on. I just want to give you a little bit of history in my gray hair.
Well, all right. So every time I give a talk, we always have people. We have two things. One thing is if I give a talk and I'm not giving a demo, when I show the demos, they say that it's in a controlled environment. I invite them to come. We have yet to have one person take us up. The only people who are taking us up on the demos are all the carriers. And they're the ones who want this so really badly. The other thing we hear is this has all been done before. And I'll have to tell you, we've reached a point after 2 months of people saying it can't be done. We show it does work. And then they go, literally the same meeting, they said, this paper, we just want to see the published paper. If you could point us all the paper, both myself, everybody who's listening, we'd love to see the published paper, love to see the results. I would imagine anybody who's achieving the results that we're achieving would have published, and I think the world would have noticed. But I could be mistaken. If there's something else out there, we'd love to learn from it, okay? We certainly do not view ourselves as having invented, everything there is in wireless. We're built upon the shoulders of giants, right? And if they did something before and there's something to be learned from it, that they forgot to tell the world that they had solved the capacity problem, we'd love to know about it.
So you're creating a centimeter cell with a small number of antennas that are distributed.
We don't know the full answer to that. I have a friend who's a physicist, and I told him about this, and he says, you're not doing that. And I said, we are, and we could show him the cell, because everyone stands still in the room, we turn off the adaptation, so it doesn't, it doesn't change, it uses the last channel state information it had, okay? And when you move it, you can see the cell edges are around a few millimeters away from the center. You can actually see the edges, okay? It's a really cool demo. And because he's been doing work at CERN and things like that. He has a whole different view of the world than we do, you know what I mean? And we were thinking it'd probably be more on the order of a wavelength, a half wavelength, something like that. It's more like a tenth of a wavelength. So we have a theory, and this is where we really want to embrace academia, bring them in, show them what it is, and get over all these questions about, it doesn't really matter who invented what, right? We just want it to be known and out there, you know what I mean? We'd like to have, I think that one of the reasons that it may be is that what you have is these intersecting waves coming in at all different angles. And what you're getting is all these slices together. And essentially, the place where there's coherence amongst all of them, when you have all these different angles and even different polarizations, these different angles, ends up to be a small fraction of a wavelength, okay? That's the best theory we have right now. We're not physicists, you know what I'm saying? We come from the world of wireless.
But you're doing some kind of adaptation, so that must be based on optimizing something.
It is an adaptation, but it's based on the adaptation of a measurement from each of these points here, based on the uplink. I mean, basically, we just take the standard uplink from LTE devices. We don't do anything different, or in the case of Wi-Fi, just a standard uplink of Wi-Fi devices. And with that, I mean, the other thing about pCell that I think people don't realize is that there's a whole series of inventions that came out of this. If you go look back to the basic concept in Dido, it's not nearly sufficient to explain what we have here, okay? And so one of the things we had to do, for example, is deal with completely uncalibrated RF chains on the uplink and on the downlink. Oh, thank you, Cindy. And so we have a system which is incredibly elegant now because we take the uncalibrated RF, the signal coming from all these different devices, to a completely, different transmit, uncalibrated downlink, et cetera. And we're able, within microseconds to be able to go and make a decision about the channel state information. And we get a lot of information. In fact, we're collecting more information than is needed for MIMO or is used by MIMO. Okay, and that is affecting our decision about what we do. For example, it allows us to create a mesh here. That's why I'd love to, if they figured out a way to do this, like say 1,000 by 1,000 array of antennas completely linearly, I need to know about that because we invented a way to solve that, obviously, but it was a very, very difficult problem. And it requires a series of practical considerations about the realities of a wireless deployment, as well as some terrific work on the math and the layering of the matrices.
When you say linearly, is that referring to complexity?
Yeah, computational complexity. So in other words, as you add the computational complexity of pCell grows with the number of base stations, or the number of radio heads, really is what they are. We call them pWaves, all right? So in a MIMO system, that would grow with the cube of the number of...
N log square n.
What was that?
N log square n.
Okay, more precisely, okay. And so in our case, as I said, we work really, really hard to make that linear. So if somebody else has got that and we can go leverage that work, we'd love to. And the other thing about it is, because of that, and the other thing you have, of course, is, if you're doing deployment across the city of San Francisco, obviously the antennas on the far end of the city are not going to be able to affect the users on the other end of the city and vice versa, right? So the way that's handled today is the world's broken into cells or clusters of some sort, whether it's cellular, cognitive radio, Wi-Fi, whatever it is, it ends somewhere, it begins somewhere else, et cetera. We don't. We have a complete blanket across the entire city. And if a user goes there with a pCell, they continue across the city, and it's seamless. And we're doing that, again, as a completely linear function of the number of pWave antennas. That was years of work to make that happen. Right? So as I said, if there's a general solution, which you get 1,000 by 1,000 matrix and in a completely linear way go and achieve some of the things we're doing, we would certainly like to consider that. All right? But anyways, what was that?
Is it possible for the pCells to operate peer-to-peer?
No.
Okay.
This is not. This is a CRAN architecture, and it is important for us to have a central control for everything. It is the case, though, that, as I said, it's a system which has one data center. It's one CRAN for an entire metro area. There are no cells. There are no clusters. Okay, it's a user-centric system. It's mobile. Here's another thing. For example, it's not sensitive to Doppler. Okay, and so it's another thing very different than MIMO. So again, if this technology is not sensitive to Doppler, that'd be great to know. But I'm going to spend the whole talk on slide 1.
Is that essential?
TDD works better. There's less overhead. We have a lot more flexibility with channel state information than has been available before. This calibration technology we've developed, turns out it solves a bunch of other problems as well. But a TDD system is nice because there's a certain amount, we have to get a certain amount of information from the downlink channel that's not available in the uplink channel. We don't need necessarily perfect information, but we do need some. In the TDD system, the uplink is simple. I mean, the uplink gives us everything we need for both pCell going obviously downstream and pCell going upstream, okay? So we'd prefer that. There's another weird thing about pCell, and this will really mess your minds up, okay? It works in existing, it works simultaneously in existing cellular spectrum without interfering with the existing cellular deployment. Okay, even if you have a completely saturated system. For example, take San Francisco, where I just mentioned, the downlink is completely saturated, the uplink is only partially loose, and so forth. We can deploy pCell we can overlay pCell over that, and that would be an FDD overlay. Okay, and we can go and then grow the capacity from there without interfering with the current use of the spectrum, even if it's currently saturated for cellular use. It's a very, very different, yeah.
How do you weave the meshes together?
I vote that we allow you to give your talk instead of interrupting you all the time.
Okay, let me get through this thing, and then I'll answer. And again, we want to have this not be the end of a dialogue, perhaps the beginning. One other practical consideration is when you're going to add a lot of different radio heads, how do you go and do the backhaul for them? when I started this project, I actually went up to Seattle and met with Craig McCaw. And I said, before I spend a lot of time on this thing, I want to understand what are the real economics of cellular. He says, everyone thinks it's the radios that are expensive. It isn't. It's the backhaul and the real estate, okay? So in a cellular system, you largely need fiber backhaul just because you have to choose, the locations have to be spread out in some sort of a cellular plan. You're never going to get an ideal plan, but you do the best you can. Sometimes you can do line of sight. Line of sight, after you paid for the line of sight radio, is free. For example, you can use 24 gigahertz or 70 or even 60 for shorter runs. But it makes it very expensive. So with pCell, what we did is we make it so you can place the radio heads wherever you like. And so what you do is you choose the locations which are economically most efficient. For example, in San Francisco, we have a partner that has done a line of sight wireless deployment where they deliver through Ethernet through the telephone closets to apartment buildings and businesses. A service that is backhauled through their line of sight mesh. The criteria for choosing a building is the landlord will let them use the rooftop for free, and it's got line of sight to another one of their buildings, okay? And they've been building this up for about 10 years, and they've got 350 rooftops, 5 milliseconds worst case latency. And they're usually getting about half of the customers in each building to drop Comcast or DSL. But of course, the buildings, we've run simulations. If you try to go and build a cellular network on top of those buildings, it's very, very poor performance because the buildings, some of them are right next to each other, some are very far apart, et cetera. For pCell, though, that works just fine. Their entire network is served by 6 fiber drops. So they have covered the entire city of San Francisco with only 6 fiber connections. All the rest of it is free. So this shows also in a stadium the advantages that we get with pCell. And as you can see, this is the traditional kind of cellular approach, whether it's cellular by doing it with LTE or with Wi-Fi. With pCell, of course, you have a small little cell around each phone. And you can expand to any density you'd like. Okay, so let me show you a couple of videos here. This is a video we haven't shown before, so it's kind of cool. We had a lot of questions about Doppler, so this one kind of shows off the Doppler thing. Let's see. Full screen here. And off we go. Hi, I'm Steve Perlman, founder and CEO of Artemis Networks, and we're here for another edition of our lab demo series. Now, what we're going to be showing you here are 16 LTE devices, iPhone 5C, 5S, and Google Nexus 5s, all simultaneously sharing 10 megahertz of spectrum, all streaming HD video simultaneously, but with only 8 pWave radios. Now, previously we showed you an iPhone running, 8 iPhones running, in 5 megahertz of spectrum, all streaming HD with 8 pWave radios. And a lot of people asked us, hey, do you need as many pWave radios as you have devices? Well, now because we're in 10 megahertz of spectrum, these devices do not need all 10 megahertz, and so they're able to share the spectrum. And the pCell technology was designed so that even with a much smaller number of pWave radios than we have LTE devices, we nonetheless can still synthesize an individual pCell for each of these devices. And as you can see, we're running YouTube, Vimeo, and Netflix on these different devices, and they're all very happily working together. All right? So another question that has been asked before is, what happens when you have an LTE radio using pCell when it's in motion? Right? Now, the technical term in the wireless world for motion sensitivity is Doppler sensitivity. All right? Now, other wireless technologies which utilize the spatial characteristics of wireless radio waves is that when you have things rapidly in motion, they are unable to work. They can only really work when things are hardly moving at all or moving very slowly. So in this case, we do not have sensitivity to Doppler with pCell technology. And the reason we don't is that we're exploiting characteristics of a distributed antenna system which are not possible to exploit when all your antennas are located in one location or perhaps in just 3 locations, for example with MIMO or cooperative multipoint. So to illustrate this, of course, people know that with YouTube, Vimeo, Netflix, any video technology, it buffers the video. So maybe when I'm moving it, the video is already buffered. Right? To illustrate that that's not the case, what I'm going to do is advance the buffer way past where I am, and then I'm going to move the phone. And as you see, the video starts right up, as it loads the buffer, just as it would if it was not in motion. And there you go, the video's running. All right? In fact, I'm going to show you something. It's going to be hard to watch on camera. I'm going to advance the video and then really shake this thing. And I'm going to move it around and so on. And when I stop, you'll see the video's happily working. So even with that kind of rapid motion, and with all 16 of these devices running at once, as you can see, pCell technology is insensitive to Doppler. All right. So thank you very much for joining us again for one of our lab demo series. And hope to have some new stuff for you soon.
You said when it stops, it started working, so it wasn't working while you were moving it?
No, you couldn't see
No, it
it.
was working when I was moving it. Do I
You couldn't see it.
You know what? The people who are viewing this, I don't know if they can go frame by frame and maybe even see it. And they'll see that actually the video, if you, you're trying to make these things concise for YouTube, otherwise people give up on them. But what I should have done probably is say, here's the normal buffering process. When you advance the video, it shows a couple of still frames and then it plays. And if you watch the slow one, I was hoping you could see that. And the fast one, the same thing. It never goes and buffers and then lets go of the video. I mean, either way, for it to start the video when I stopped moving, it had to have buffered it. You know what I'm saying? But it was playing the video while I was doing it. It's kind of hard to see. That's why I said when you're moving very fast. But again, the best thing to do is come to the lab. We have nothing to hide. You know what I mean? But clearly, if this, like cooperative multipoint MIMO, I think it's well known that if you have things fast motion, you can't use them because the channel state information you collect is obsolete by the time you actually try to go and turn around and form your signals, to synthesize your signals. So again, how long do I have till? 5:30. 5:30. All right, I'll show you one more video, which is one that's been up there, but nonetheless, it just shows the capacity we have. It's a little less technical, and that's on this here. And I'll try to maybe fast forward to the good parts. Let's see. So here I'll introduce what it is, and then I'll just kind of zip ahead, because it takes a little while to get the video started. If you want to watch the whole thing, it's on YouTube. Hi, I'm Steve Perlman, founder and CEO of Artemis. So what we're going to show you right now is the technology behind pCell. And we're going to show you that by using actual lab radios instead of using, a LTE radio that's a commercial product. The reason we're going to do that is it allows us to go and show you the actual signal that's going through. And it also allows us to turn off certain things built into LTE, like for example, error correction. So if there are any imperfections, you'll see them because we want to show you them, all right? And you can see that each of these PCs back here, and these are tablet PCs, we're running Linux on all of them. And then on the back of them is a lab radio that allows us to go and be exactly like an LTE receiver, with the difference being that, of course, as I mentioned, we're able to turn off the features that would normally make it a cleaner signal and also allow you to see what's going on, all right? So first of all, what's happening now is we don't have pCell technology turned on. All the pWaves that we have in the room are transmitting the same signal just as if they were in a conventional cellular system. So what do we see here? Every device has the exact same video playing because that's what happens when everyone's transmitting in the same spectrum, the same signal. So you can see we've got 6 different videos playing. The other thing I want to point out is this little white box here. That's called a constellation. Now, a constellation is what is used by radios in order to go and take the waves coming in, the phase shifts and the amplitude changes, then map them into a graph. This is something called a 4QAM or QPSK. It's the simplest form of it. And those little dots are all happily in their little quadrants, in their corners. That means you've got a good signal. If they get all scattered about and you see noise, that means you don't have a signal, all right? So as you can see, all of them are very happily receiving their nice QPSK signal in their constellation, and they're all displaying HDTV, all right? So now what we're going to do is flip on the pCell technology and watch closely, because now each of them is going to get their own private pCell around their antenna, and each of them then is going to receive a different video. So let's flip on pCell technology. And there you are. All of them are still getting their 4QAM signal, their QPSK signal in their constellation. The reason they're a little bit noisy, this is lab radio equipment as opposed to commercial equipment. That's why you see a little bumpiness. The normal signal you see is actually quite clean. And then the other thing you could see is that if I pick one of these guys up, the signal keeps on going, all right? You see it adapts. The little pCell that's around here is following the radio as I move it around. Now notice what happens if I put the antennas right next to each other. So I got this guy and this guy connected, okay? No problem. You can have the antennas that close and they're still independent. Let's suppose I get 3 antennas close to each other. All right, so I got antenna back here, antenna back there. 3 devices that close together. The pCell technology is so specific as to where it actually delivers the pCell that you can have devices that close without them interfering. All right, so now I'm going to show you something that's actually really magical, and that is a chance to actually go and see a pCell in space. But you're going to have to work with me on it, all right? So let me show you how we can demonstrate it. Now, obviously, the radio waves are invisible, all right? So the best I can do to show you where a pCell is kind of to go map out where it is and where it isn't. So normally as I move it around, you see how the constellation stays together and the video plays, no problem? All right, I'm going to turn off that feature of the pCell system, which is what we call the adaptation, right, which will move around the pCell as we move around the device. And I have to hold it very steady, and if I hold it steady, the video will play. But as soon as I move it, even the slightest amount, you'll see it will move out of the pCell and back in. All right, so let's turn off the adaptation. So everything plays fine. Now watch when I move this guy just a little bit. See? Constellation breaks up, video stops, move back, video plays again. Move a little bit to the side, constellation breaks up, video stops, and move it back in, there's the video again. Move it down, move back up, there's the video again. Move it up, there's the video again. Move it towards you, and it breaks up. Move it back down, move it away from you, video breaks up, moves it back down. So there you have it. So literally what I just mapped out, going forward, backwards, up, down, left and right, is the shape of the pCell. It's about 1 centimeter. Okay, so let's turn on adaptation again. Now watch as I move it around. It follows, all right? So that's the magic of what we've created here. We've created individual cells which follow you. All right. So I didn't quite know where to break that. Yeah? What was that?
Your tablet, one of the PCs started breaking up too.
Because we changed, we've done demos of that. The other demo we did, that again would be too short, is I just hold it steady, and one person takes a step forward. It changes the channel state of the whole environment. And so by moving the tablet, I was changing the channel. It depends where the waves are. I mean, you could have someone walk right here and nothing changes, or you could have someone lift a finger and all of them go nuts. It depends on the multipath in the room, right? So it's interesting. It's an area of study that I think is going to be a lot of fun. But let me go and get back into the presentation here. So, and we'll go here. All right. So we showed the demo. Okay. So this is one of the things about cellular that just inherent in the way. This is from Ericsson. This is they had a little report they did last year. And people don't realize that while cellular was a really, really good solution for telephony, because you end up with this low data rate on the edge, cellular only works well for data near the cell centers. That's true whether it's a microcell, or a small cell. Because in order for cellular to work, it has to taper off performance. So the average performance of a cell is about 1/10 that of what the peak performance is. And of course, as Ericsson points out, by the time you get to the middle of a cell, it's very difficult to do much more than music or the web. And by the time you get to the edge of the cell, it's very difficult to do much more than telephony, voice, and things like Twitter. Telephony messaging and things like Twitter. Whereas pCell, what's significant is that you're creating these cell centers all over the place. And we're getting peak performance throughout the coverage area. So even in a small cell situation, suppose that small cells didn't have interference issues and didn't have intracell interference and didn't have handoff issues, it's still the case. This is a vastly more efficient way of deploying wireless. When we put pCell radio heads at the exact same location as cellular antennas in a cellular system, we right there get a 10x increase in the average performance. But most importantly, beyond the overall capacity increase, what we do is create a very, very consistent throughput. All right? So you can see this in terms of this simulation that we did. We were showing this before in a previous talk I gave. But anyways, this shows an ideal cellular layout. It distributes phones throughout the area. And then we'd run the MATLAB simulation. There's these characteristic volcanoes, as we call them, where you have very high SINR, and then it has to go and taper off towards the edge. So we gave cellular the benefit of the doubt here. This is like in Kansas as if it was in outer space. I mean, so there's no shadowing, it's just simple showing it, because we want to show a nice clean signal here. And then as you can see, user number 1 happens to be right near the cell center. They're getting terrific performance. User number 2 is between 2 cells. And so, well, too bad for you. And then everything in between. And again, if you average it out across the area, you find out you're getting about 1/10 the performance of the peak of, say, what user 1 or 6 is getting. Now, for pCell, we're using the real 3GPP shadowing and path loss model here, because we want to be as bad case as we can be. And we've actually found that it models it's a pretty good model to use for the outdoor work that we've been doing. And anyways, and the indoor work. But it has all the shadowing and all the other issues, which is why it's a little bit more noisy. But anyway, as you see, with the exact same antenna layout, the exact same user device positioned, we're getting a peak for each of the user devices. And so you get this very uniform performance throughout the coverage area. And that's the 10x increase. If we go and cluster the users, you see you get this problem where not only do you get highly variable throughput depending on where they are on the volcano, but of course they're all sharing the same capacity. In the case of pCell, almost all the devices are getting peak performance. And as you can see, the reason this is possible is, of course, they're getting the benefit from the faraway antennas. These guys here are only getting the benefit from this antenna. These other antennas can't help them at all. And we've seen, this is not just an issue of people being able to watch videos where they want to. This is a public safety issue. When the bomb exploded during the Boston Marathon about a year ago, the AP reported that all the cellular networks were told to shut down their service to avoid using cellular to detonate another bomb. 2 hours later, they retracted their report, saying it was a rumor. Okay, what happened was that, of course, you have one cell covering that area for every one of those carriers, all the 4 carriers. And every one of them, people were pulling out their phones saying, I'm either okay, I need help, or people trying to call in, and so forth. It jammed the service. There are no more payphones, okay? So they created a dead zone, utterly unusable zone. In every, 4G, 3G, and so on, every class of service was overwhelmed. And that's a significant issue. With pCell, if something like that happened where we had a sudden burst of activity, I guess if you looked at it, you'd see that the power would rise up on the further away antennas. But of course, much more complex stuff would go on, and you would be able to serve users even if they're clustered very close together. Yeah?
Cell density and the same transfer power per cell in pCell?
Same maximum transfer power. And that is, actually, I don't know. I think the transit power can be higher in this case. I'll have to check. I don't remember, to be honest, because the thing that we do need less power than you would think. And the reason is because of maximum ratio combining and things like that. We're getting a benefit from a summation of these different antennas. Whether that benefit is enough for this guy to reach all the way to there, I don't remember. And Antonio did the simulation. That's a good question to ask him. But the thing about it with cellular is that there's times when you want to transmit with more power, but you can't, okay? And, but the simulations, if we get to it, that I have, we do match power for power. We have the same, and I can show you what it's like, a cellular system versus a pCell system with the exact same antenna locations. I'm not sure if this one is that, okay? This one we were just trying to show what you could do in kind of real deployment and kind of illustrate the bumpiness of cellular and versus the uniformity. Because it's not just all about capacity now, it's also about, if you want to deliver media, you need uniformity. So,
just to clarify, you
yeah.
said you're using maximal ratio combining. How is that used here?
It is used, it's used both, well, okay, so we have these antennas here, and this is where you're crossing the bridge between perhaps not my depth of knowledge of wireless and Antonio's. I'm a little more of a conceptual thinker, so if I've used the term incorrectly, I apologize to everyone. I think I've used it correctly though. We have, each of these guys is receiving a signal from all these different antennas. Some of the signals they receive could theoretically be below the noise floor, and the summation of the signals add up to something more. On the uplink, for example, I do know, because that's actually one of the big features of the system, is that on the uplink, the received signal from all these different antennas the received signal from, say, user 2 on, I don't know, on this antenna may be too low for it to really receive much. And it is able to go and utilize the data together, utilize the signals together and combine them. And from that is able to get a higher data rate while operating at a much lower transmit power.
So that's what the pCell is doing? Is the maximum ratio combined?
So I think that the correct answer to that question, the exact answer to that question, we better answered by Antonio. I wish I'd brought him. But actually, maybe Cindy, you can call him. And maybe we can give you the answer before the talk is over. All right, he could just
You're
join.
in a dead zone right here.
Oh, I'm in a dead zone?
Yeah.
No, maybe can you ask him whether or not? What? There are. There's a variety of techniques that can be used to statistically combine the signals. I do know this, that when we're doing the uplink, the received signal here to a given one of our radio heads can be below the noise floor. Yet the aggregate of the signals can allow us to resolve the signal.
You mean for the pCell, because that's the Wi-Fi, right? So is it?
No, this is cellular. Cellular and Wi-Fi, it works the same way.
So the maximum ratio combining is part of what your pCell technologies do.
If that is the right name for taking signal to multiple antennas that are distributed and combining the signals together so that the statistical aggregation of the signals goes and results in a higher power signal or a better SINR signal. I should better memorize.
That's done on the uplink on all of those.
It's on the uplink, and I think what we're doing is on the downlink, we are getting the benefit from the aggregation of the antennas.
I can believe that.
But there's more than one technique that I think can be used for that. I don't know if MRC is exactly the technique.
That would allow you to isolate the users in their own little cell if you're using the antennas just for combining.
Oh, no. That's not. So I think your question was, are we using MRC in order to go and create the pCell technology? And the answer is no.
Oh, I thought you just said yes.
No, I said we're using that to go and allow us to go and allow an LTE phone's battery to last longer. So if you have an iPhone, it might last 2 days or 3 days in a pCell network rather than in a cellular network. Because in a cellular network, if you're very far, if you're on the edge of the cell and you spend the whole day talking on the phone, your thing's transmitting. And some people wonder, why does your phone burn down some days and other days it lasts forever, right? Okay, so with pCell, if you've got this, whether you're on the downlink or the uplink, you have very high SINR. So the power requirements are very low. The demos we just showed you are at 1 milliwatt, right? Even indoors, 1 milliwatt's not a lot, okay? Okay, well, either way, it's sufficient for our demos. Okay, I don't. But as I said, it's.
Again, I suggest we allow him to finish his talk.
Only one question per slide. We moved twice the slide.
Okay, so this goes and shows serendipitous deployment. That is to say, where the antennas are spread about, where it's the least expensive. We gave the benefit of the doubt for cellular to make the users kind of randomly scattered. Of course, in this case, here the question about power comes into play here. This cell can't increase its power. You'd like it to be able to, because it would run into that cell because they're too close together. This guy, again, each of them is bounded on some edge. So you end up with extremely low performance, even if you have the users completely spread out across the coverage area. With pCell, it really doesn't matter where the antennas are located. You're still creating a peak of SINR wherever the users are located, all right? And, okay, so the other thing we did is just make it compatible with LTE and Wi-Fi devices. We can work in licensed or unlicensed spectrum. And for example, Wi-Fi obviously is unlicensed spectrum. We could do, a carrier can gradually do pCell deployment, and then we do a handoff on the edge of the pCell coverage area to cellular, or they could do a whole large region if they'd like to. In the US, what the conversations are largely about pCell deployment and then handing off to LTE on the edge. It's interesting, in other countries, particularly we're seeing in Southeast Asia, there is a huge interest in not ever deploying LTE, or they've done a little bit in their cities. But the idea, they want to deploy pCell. It's much less expensive from a capital equipment cost, CapEx, and also from an operating cost. They can build devices that are pCell only that do not have all the stack that you need for a cellular system, and so they're much less expensive. And then they would build phones which would hand off to 3G. They already have 3G, maybe 2G networks, et cetera. So so it's interesting. Again, one of the unexpected results after our announcement is that people are thinking about skipping LTE altogether in entire, very, very large nations. So you can do things with MVNO. I mean, it's public knowledge that we've done an FCC filing with Dish. I can't disclose anything about the relationship, but I think it's obvious to everyone that they have lots of spectrum. They have 50 megahertz of spectrum, but they have no infrastructure. So for operators like that, okay, obviously this is a much less expensive, much lower cost option, and they can begin to deploy it. Because they're compatible with LTE devices, they can begin to deploy it in major, major metros, other places with a high congestion, and then use MVNO to hand off, to another operator until they finish their deployment. Okay, so this shows the CRAN architecture. It's very conceptual. It's a completely software-defined radio system. The fact that it runs in real time, the demos you've seen, we've been running on, two dual 8-core Intel machines. They're running Linux. And we're using National Instruments USERPs from, what's the answer? Yeah?
That's the answer. But the cells are transmitting, the average power is the same, but the further away cells transmit higher and the closer cells transmit lower. And then the other question, I just couldn't word it.
So was it the other question what?
The other question, I couldn't
You
word
couldn't make
it.
it. Okay, so the answer in that MATLAB simulation you saw, the further cells are transmitting at higher power. Okay, in the pCell version. Okay, so it's a full software-defined radio implementation. I do not think we could have designed this if we were not using software-defined radio. The iterations we do per day are just amazing. It's been a revelation for me. I'm just seeing what we can do, and a lot of it was very fundamental work on doing the low-level code, particularly in the physical layer. To make it all run in real time. This shows a diagram of what you might do. This would be like the CRAN, or we call it DRAN for want of a better word, the data center. And we typically have been doing deployments. When we do our testing, we put 8 antennas on a rooftop. It depends how big the roof is, obviously, but that seems to be pretty good spacing for getting it going. And so you can imagine, 10 gigabits fiber going. You could have fiber to a rooftop, or say 10 gig to a rooftop, then line of sight through some mesh like this. Okay. If we're talking about TDD in 20 megahertz, we get about 70 megabits per second of downlink, and each pWave radio, or each radio head, adds 70 megabits per second to the aggregate capacity of the coverage area. So if you have 10 of them, you'll have 700 megabits per second. If you're 100, you have 7 gigabits, and so on. And then that aggregate capacity is shared by all the user devices. Each device obviously is limited by the Shannon limit, so it can only receive to each antenna 70 megabits per second. If it's a 2-antenna device, you can receive 140, and so on. And you can then divide up the capacity any way you'd like. Some users can be getting everyone can be getting 10, you can be 5, and so forth. But the thing about this that's very significant, that's very different in cellular, is that when I say that each of these pWave radio heads adds, in this case, 70 megabits per second of capacity, it's not 70 megabits peak. That's pretty much 70 megabits average. There are some factors that make it slightly below average. It's not perfect. You saw the MATLAB simulations. There's a lot of details. But it's way closer to peak than it is to anything else. So it's a very efficient way of deploying deploying a radio system.
I'm getting kind of impatient with not hearing what he wants to tell us.
Yeah, well, this is an academic seminar, which means there typically are questions. Okay, so my question is, how are you isolating each one of those devices? Can you, in terms of getting this spatially isolated pCell?
It's entirely based on the uplink. In the case of the uplink from LTE, it has some, very convenient waveforms. There's SRS, there's, CMRS? I forget what the other one's called. There's a couple things it does, which are nice because they're orthogonal to each other and so forth. And they're designed for this very purpose, but they're just not calibrated. They're mainly meant for kind of rough beamforming, okay? But because of this technology we invented, we are able to use them to get a absolute precise, 16 bits of resolution, precise channel state information, as if we're right there, but using reciprocity. It's very exciting, okay?
Can you beamform to each individual device?
We don't beamform. We create, not beamform either in the ArrayCom view of the world, where you kind of aiming beams, like in a phased array antenna. I'm not giving them justice. They've done a lot of work beyond that.
It's a phase array.
It's not a phased array, and it is rather a complex combination of these different antennas. As I said, there is no single group of antennas that serves one group of users. For example, suppose I'm a user here, and I've got a group of, each has got a group of antennas. The group of antennas are actually interleaved amongst each other, okay? And so this antenna here might be serving this user and that user, whereas this antenna here is only serving that user, this antenna is only serving that user, all right? And I don't know, a big truck comes by, and now this antenna for 1 millisecond is not serving this user, and then the truck goes away, and then it is. Okay, it adapts at that level of resolution. In fact, when we do pCell native, where we're able to go and do a protocol that's not limited to the LTE frame structure, we can do it on microsecond basis.
So isn't that distributed mining? I mean, I know someone else asked that, but that's my understanding of what distributed mining does. Is you have a whole bunch of antennas, and they're figuring out the optimal use of the antennas to serve multiple users.
So the distributed MIMO systems that we've done, we looked at some of the work done, I think at USC, is that?
It's been done all over the world. I mean, it's actually, yeah.
Okay, so we've looked at all those papers, we've seen the different things. We haven't seen anyone who's been able to achieve this capacity, this level of linearity, been able to overcome the lots of other challenges, near, far, and so forth. I mean, again,
You can go and visit him. He's in Palo Alto.
We're in San Francisco now. Yeah, we're doing city tests. But please, all of you, everyone in this room, I would love to organize a field trip. Come here, ask all the questions. We got so many whiteboards. We have the PhDs there who, when it comes to the very, very deep questions you're asking, can answer them better than I do. I'm more of a conceptual generalist. You know what I mean? And I am. But let me just get through a couple things, because this is more of a computer sciencey thing that I really like, and I think that it's a new thing for wireless in a way. So the way this shows actually what's happening inside the system. We have virtualized wireless. If you see, here's the user devices, and you can see the pCell around them. The pCell is really around the antenna, but I think you know what I'm talking about here. They're all, in each case, they have an individual channel, okay? In this case, we have 8 user devices, and in that case, we actually have what we call virtual radio instances. So in software, we've implemented, in this case, 8 eNodeBs. eNodeBs, you might or may or may not know, is the name for the stack that is in the center of a LT cell, okay? And so we have then these pWaves distributed, and as I was saying before, these guys go and uplink their signal. All these guys hear that signal, and remember, they're scattered about, and they all receive that signal. We pass back the information to the data center. And then simultaneously what's happening is these eNodeBs each are going and creating a completely separate LTE signal. If you would take take this signal here, digitize it, have an A to D, D to A, and put an antenna out here, the phone in your pocket would try to connect to it, okay? So we have 8 simultaneous LTE signals that are being created digitally here. They feed into here. And then what we do through this processing is we go and do a spatial mapping between one of these eNodeBs and a device. For example, VRI3 appears at the receiving point of the antenna of user device 3. And VRI6 appears right here, okay? And literally, if you take a piece of LTE test equipment, that's what it shows. And it will actually show that, I'm all alone here. There's no one else using any of the resource blocks, and I have the full channel to myself, okay? Now,
Require new systems,
that's on the next slide. I love it when people ask a question, I say, here's the next slide. So you, obviously, not every, take 70 megabits per second. LTE was sized, LTE bandwidth, everything was sized for many, many users sharing one eNodeB. So clearly what we're doing is, unless someone's got a ridiculously high data rate application, for mobile applications, we're way over delivering in terms of capacity, right? So we can go and divide up that capacity using either OFDMA or TDMA. And in this case, it shows OFDMA. And here we've decided, okay, none of these users needs more than half the throughput of the channel, So let's go put half of them on the lower band and half of them on the upper band, okay? And so here you have the green users, obviously in the upper band and the lower band, and the system is able to so with 4 pWave antennas, here we are serving 8 users. Simple enough.
Ratio, right? As the number of users, as the density increases in a certain area, you'll need to put more and more P antennas in that area, I believe.
No, it's related to the data demand in the area, the data rate.
Well, assuming each one just continues to keep the same data demand, then you'll have to kind of go and put more and more of your antennas in that.
If it's the case, you really, but think about it. I mean, you know, we're talking about increasing, just by deploying these pWave antennas at the same location as current cellular antennas, an operator gets a 10x increase in capacity. So it takes a while to fill that well. And then yes, if you want to go beyond that, you can start adding more. But 70 megabits per second, or, you know, which is, again, 20 megahertz is a reasonable deployment. Some are 10, but most are 20 or 40, right? You know, is more than, it's hard to think of mobile applications that really need that much throughput, okay? And so most of the users are using much less than that. So in this case, I mean, honestly, so here we've got 8 times, this would be 560 megabits a second. I don't know, you know, that probably is enough capacity for probably, for support 200, 300, 400, 500 users. You know, it's hard to know. But let me show you the other way we share, and that's TDMA. And then in this case, we go and share some in one, this would be say 1 millisecond, and then another millisecond we would go and share with, distribute to these users. And of course, those techniques can be combined. Now, a more complex thing to explain is like what happens to these guys when they're not getting, there's not a pCell around them, okay? And we've solved that. It's just, honestly, I think it would go beyond the scope of this talk, but it's a question that can be answered if you'd like to come and visit us, okay? I don't want to dismiss it. It was a difficult problem to solve, but we solved it. So that these guys stay alive even though they're not being spoken to, okay? Or I should say stay attached. And then the best thing about pCell is we can handle multiple protocols at once. And this is very, very exciting. Here we have the VRIs are not just eNodeB release 8, say, which would be limited to 64 QAM. You could do release 10, you can go to 256 QAM. And because we're getting such SINR, that's actually a realistic, it's a realistic coding scheme that we think we can achieve, although we don't have release 8 devices just yet. And also, we can do something we call pCell native. A pCell native device would have a tiny fraction of the complexity of an LTE device. I mean, there's no MIMO, so we don't need any MIMO processing. The device, there's no shadowing, so we don't need receive diversity or transmit diversity. There's only one antenna needed. Okay, so only one RF chain. And we don't need anywhere near the level of error correction. I mean, that demo you saw, you might have seen the video drop out once in a while, even with the lab radios, but hardly ever it did at all. And there's no, there was no, all the turbo coding was completely turned off when the demo I was showing. So we've got a very robust system. So it means that now you can make a phone which is much less expensive. And so we've been talking about pCell phones that are just pCell, and then I don't know, if you go out of the pCell coverage area, you're stuck with maybe Wi-Fi. Or interestingly enough, pCell phones, which are pCell, and then when they go out of the coverage area, they have 3G. 3G is a very mature technology, one chipset pretty much supports all the protocols and so on. All the patents have expired for the most part. So it is, this case, user 5 would be receiving in the same spectrum, using the same infrastructure, pCell native. User 4 would be receiving release 8, they'd be limited to 64 QAM. Meanwhile, user 1 over there would be receiving release 10. We don't use any of the LTE advanced features other than the higher coding rate. All right? So, yeah.
What is the failure mode? What is the failure mode when you run out of capacity?
Well, it does is it begins to divide up the users the same way, TDMA, CDMA. At some point, it'll be just like, it'll be similar to LTE in the sense that your performance gets worse and worse, right, as you get less and less capacity. But there's a difference. I mean, there's an upper limit. I think it's about 200 or something for what an eNodeB can support. Because everybody's getting their own eNodeB, we have no upper limit in terms of the number of users. You can just keep adding VRIs. So it won't go dead on you. You won't go and say, hey, dude, you can't even connect, all right? It'll connect you. Whether your device feels it's being starved at some point or not, is of course how the device is designed. And different devices we've tested actually have different starvation behavior, okay?
So if you're making a phone call, would it break up?
Oh, okay, so I think what you're asking is a different question. That's a quality of service question. The scheduling algorithm that would tell this system how to allocate, when the system is oversubscribed, there's more data demand than the system can handle, okay? Then it comes down to the scheduling algorithm, how you do it. It's very difficult. I'll tell you, I have huge admiration for the scheduling algorithm that's been done with cellular and the SON technologies that have been done, because it's a really, really hard problem, because you're not just dealing with sharing a limited resource. You're dealing with a limited resource that has an exponential drop in performance as you get toward the edge. So the question is, if the guy's on the edge, he's watching video, should I let him keep watching video? Because he'll take down the rest of the cell, he gets further from the center, right? Or do I cut him off? And so those are the kinds of questions you have to ask in a cellular system. The nice thing here is that everybody throughout the coverage area is getting high SINR. So the question is more like a scheduling algorithm for a CPU in an operating system, or as I said, this is really like a virtualization of radio. Another way to look at this, I mean, the OSI model goes down to level 1 for the physical layer. In some ways, pCell is like level 0. I mean, because this is level 1 right here. Well, what's underneath level 1? Right?
The radio heads, they have 8 antennas, is that what you said?
The radio heads each have 1 antenna. There are 8 radio heads. There are 8 radio heads in this example, and this.
So so there's only
in this
one
example,
antenna.
there's four antennas, and there would be 8 users.
And what type of antennas are they?
What we're using right now is little dipoles. The spectrum that we have for our use is we have some 2.6, we have some 2, some 1. I haven't. It's about. We haven't. Okay, we have some other. We have 900 as well. Of course, is open for us to use. Okay, then let me show you some simulations. So release 8. I'm just about out of time. Is that right?
Keep going.
Okay.
We'll just cut off the video from the outside world.
All right. So release 8 allows you. This shows Sprint's locations in this coverage area, which is downtown San Francisco. Our office is in the lower right corner. So release 8 allows you to go up to MIMO 4x4. Release 10 8x8. So then we showed what would happen with 30 megahertz spectrum and 2.5 gigahertz and 20 watts. And we also, for MIMO, for release 10, we go all the way up to MIMO 8x8. Sprint's not using MIMO 4x4. There's no 4 antenna phones that exist today that I know of anyways. Certainly no 8 antenna phones. But we want to still give LTE the benefit of the doubt. For pCell, the model shows a real phone, which is just a 2 antenna phone, which is like the minimum number of antennas the LTE spec allows. And we also want to just show a comparison. So here the power limit is the same, per your question before, 2.5 gigahertz. And then here it's 1 watt is all we're allowed to use at 900 megahertz, obviously. And we only really usually find 15 megahertz. We didn't want to use the entire band, so we put 15 megahertz for this.
You have 8 radio heads?
8 radio heads, but it'd be like 8 radio heads spread a few feet apart. You know what I mean? As opposed to separate buildings or other things, which give you really nice angular diversity. So we don't get quite as much angular diversity as we would if we were as when we're doing a more distributed deployment. But this goes and shows you right here what happens with the 32 locations that Sprint has in this location. And as you can see, we modeled it with 100 users per cell. So these are pretty heavily loaded cells. And you can see they're saying 0.6 megabits per second per UE. Even if you go to LTE Advanced, and now you're doing MIMO 8x8. This is MIMO 4x4. MIMO 8x8, it really doesn't get that great. If you look at pCell at the exact same locations, again, going to a 2 antenna phone, a real phone that exists today, we're getting 6.7 megabits average. And it's really kind of fun that 900 megahertz at half the spectrum at 1 watt. It just shows how great UHF is compared to microwave. You get 4.2 megabits a second. Then we go over here. These are the real rooftops. Remember I told you about our buddies that have these line-of-sight rooftops? And you can see just how random they are. I mean, they're just scattered, okay? It's completely serendipitous. As you can see, and we're still at 100 users per cell, so it still is a very big load on it. And as you can see, when you have a random arrangement of cells, the performance actually goes down in a cellular system, and even as it does with a LTE Advanced system. In the case of pCell, as you can see, the performance actually goes up. Why? Because we just have more locations. Then the reason, by the way, the red area can't really fill in is we are limiting the power. We'd like to use more power where we have a wider space there, okay? In the case of 900 megahertz, again, the performance goes up with the more dense locations. And this is even a more telling diagram. This really tells what the users experience. You can't see the numbers from the, probably can't see it from far back, but right here is 35% of the users are getting 0 throughput. Okay, and then this shows the other users, again with LTE. It gets a little better, 20% are getting 0 with LTE Advanced. But you see pCell has a very good rate, except in those areas that just are too far away. Only I think about 3% are getting nothing. And then at 900 megahertz, it's amazing. About 7% of the users are at peak performance for of what is available. Then if we go to 220 rooftops, again 100 users per cell. This is a at 220 rooftops, 100 users per cell, this is a massive deployment, okay, in terms of capacity. And as you can see, 40% of the users are getting nothing, and then a few are getting something. And LTE Advanced, again, 40% are getting nothing. LTE requires you to have a nicely arranged arrangement of buildings, of cell locations. And again, as they get closer, you have this big intercell interference problem. Then with pCell, as you can see, the performance is quite uniform, and it actually leans toward the peak. And as we get to UHF, once again, a full 20% of the users are getting full peak performance. So then this shows SoftBank in Tokyo. They have a thing called, they adopted this antenna system, distributed antenna system called, for wireless city planning, they call it, is the name of the service. And they have these 8 antenna things, and because they have fiber everywhere in Japan, they backhaul to these broadband hotels, and then they have these line cards which do LTE. And it's pretty awesome. I mean, just look at this coverage they've got. And here we modeled everything under the sun. MIMO 2x2, 4x4, 8x8, MIMO 8x8 with cooperative multipoint. You'll see some of the benefits of cooperative multipoint when you combine with MIMO 8x8, but I think it's an extreme situation. The conditions are the same as we did for the last one, except for the power here. Here, they can't go much beyond 250 milliwatts. If they do, they obviously spill into the adjacent cells because they're so tightly packed. So it's kind of like Wi-Fi, okay? And with pCell, we do model 250 milliwatts, but we only do it with a real phone, one that exists today, a 2-antenna phone. And then we also, because we model it, what would we do if we had 5 watts, okay? Because we can overlap, all right? And so again, it's very telling. If you look at MIMO 2x2, you're really getting very, very low performance. It is 1.1. You'll see in the next slide, there's only a few users who are getting anything. Gets a little bit better with 4x4, a little better with 8x8. Cooperative multipoint with 8x8 does give you a little bit of a benefit here. But I mean, you're talking about a phone with 8 antennas in it, and then a very, very sophisticated communication system. The other thing with cooperative multipoint, MIMO's sensitive to motion. Then you add cooperative multipoint, it's very, very sensitive to motion. You're at 2.5 gigahertz. You're talking about people that are not moving, that are on a cell edge, that this really benefits. It's kind of a weird situation. Yes?
So these are model numbers as opposed to measured numbers?
Model numbers. I don't know. Well, okay. But we have run with all the carriers that we've done modeling with. We've spoken with their technical teams, and they've said that our models that we've done for their cellular systems are fair. So we have our confidentiality agreements. I think anybody who has modeled a cellular system in the United States, if you put 100 users per cell, this is the results you'll get. Okay, but anyways, again, if the model's not correct, or somebody feels there's another way to look at it, we'd be very happy to go and change them. But it's our goal is to go and try to be as accurate as we can. We were using the 3GPP shadowing path loss model for both cases. In the case of pCell, what we're seeing with 250 milliwatts, which the same power as these 4 simulations, is 35 megabits a second. When you let us go to 5 watts, it really is something astounding. This is what we'd like to eventually get to, which is, complete coverage near the maximum throughput across the entire coverage area. And you can see that with these, again, the modeling. With 35% of the users with MIMO 2x2 and 4x4, there's 0 throughput, and all of the data rate comes from a few users, of course, that are in terms of average data rate. Again, MIMO 8x8, we're modeling it, okay? I just don't think anyone's ever going to build 8x8 phones, and then cooperative multipoint does help. okay, because it gives you about, I think, a 30% uplift on the cell edges, which is a big issue for this. When you talk about pCell at 250 milliwatts, that's our performance, and this is what happens at 5 watts in terms of where we go. And as you can see, a full 10% of the users are actually getting the maximum data rate, which is about 53 megabits per second. All right, so as far as our business, there's no significant technology risks that remain. It's been 10 years of work of just solving one challenge after another. A lot of people have asked us, what is the one thing you did? What's the one invention? I wish there was just one. There was some core concept we came up with, but it needed to be made practical, which took years of work. And then after it made practical, we need to make it commercial ready, which included, for example, making it compatible with LTE and so forth. We wouldn't have bothered solving the calibration issue if we didn't have to work with existing devices and so forth. I mean, that in itself has value, I think, to the wireless world, even independent of what we're doing here with pCell. But all these problems had to be solved so there's a deployable system. That's, again, my view of the way we do things. Obviously, devices exist in the market. There's no spectrum work. We can look at licensed or unlicensed spectrum. This is another discussion we're happy to have with you. Again, it's a bigger discussion than I can do in this meeting. It's tricky, but we have a way that we can make use of existing spectrum. So for example, the 700 megahertz spectrum, which is completely saturated by carriers. It's actually kind of amazing to watch it through the day. It's great spectrum, but it's saturated, okay? We can simultaneously use that spectrum without interfering. We can deploy in small or large areas, and we don't really have competitors right now. And we've been contacted now by half of the mobile operators in the last 2 months. There's $1.2 trillion of revenue that's brought into the mobile operators worldwide. We're just a little company, and we are just overwhelmed. Operators representing 600 billion of that have met with us, all right? And we're actively engaged with, as you see, 2/3 of them right now. We've been doing due diligence. We've gone through this whole process where people are attaching the stuff to it and seeing whether or not it works and so forth. And we've often had the things said that they've never seen such good results with their LTE analyzers when they're looking at what they're seeing. The other thing we've been connecting with is all these non-operators. It's actually most of the people we're speaking to. And again, you can't really. We try to measure it in the number of companies we're talking about. We said it's easier just to look at their annual revenue. It includes stadium holders, spectrum holders, mobile platform holders, mobile device makers, mobile silicon makers, infrastructure players, the people who own the real estate. We've had 3 separate companies propose to offer us rooftops in Manhattan. It's overwhelming. It's just been crazy. So we'd like to do our first LTE and Wi-Fi launch, and venue Wi-Fi, we call it, launch in the 4th quarter. It depends on who we work with and exactly how it comes together. And then we can do a widespread deployment. In other words, hand it to them to do deployment. We see our business perhaps being more like a Dolby in the end of all this. Let other people make the infrastructure and let the other people be the carriers, put in the servers and so forth. And what we would like to be is a software-defined radio company that provides the software that runs on these servers. And that is it. Thank you very much. I'm sorry I ran over.